All right, hello Patriots. This is Mr. Love, aka the Math Patriots, bringing you another fun lesson from the awesome, exciting world of high school math. Recording slightly differently today because today is an A day. I know for sure I'm going to be out on a B day. So all of my B day students, hopefully the sub is showing you this video and you're not just sitting there doing nothing. So we're going to go through the benefit of me doing this live with my period 4A is that there's a lot of writing on this stuff, okay? You're going to have to be doing writing. You're going to have to copy stuff down. We've got to keep the pacing going. And since I tend to want to go too fast, I've got a live class in front of me to tell me when y'all are done writing. And hopefully the A-Day, B-Day stuff goes on. Also, sub, if you need to pause it for a few minutes or for a little bit so they can finish writing before I move on, that's fine. Just, we can't take too long. Because as of right now, as I stand in my live class, I've got 54 minutes to finish this, and I think we'll have time. But if you're starting this with only 45 minutes left in the class period on B-Day, that's going to be a problem. Also, students, if for whatever reason you don't finish this in class, it's on the playlist. You can always jump in and finish it later. So, all right, I told you guys last class period that we're going to be starting up with proofs today. Now, the awesome part about proofs is that I kind of told you y'all are going to have a awesome experience with some of the older people in your life where you tell them you're going over proofs and y'all can kind of cry together. So did anybody do that? I'm curious. Anybody actually talk to their parents and tell them we're doing proofs? All right, what'd they say?
Well, my mom hated it, but my dad liked it.
Okay, mom hated it, dad liked it?
My mom was like, oh, you have to study a lot to remember them.
Okay, all right, Lily?
My mom said ew.
Said, ew. Okay, here's the thing. My grandparents, I talked to them about this when I was in high school. They did proofs, and they hated it. My parents did proofs. My mom hated it. My dad was a weirdo like me. He was a math teacher. He loved the stuff, okay? I went through geometry at the time. I absolutely hated it, okay? Guys, you got to realize that you are now members of the Great American Geometry Society where everybody has gone through this thing, and we all either loved it or hated it, but either way, it is still going to be this awesome rite of passage that when your kids get to be freshmen or sophomores in high school and they come in and say, Mom, Dad, I'm doing proofs, you can sit down and comfort them along with them because you knew exactly what it was like, all right? This is one of those few things from high school that everybody remembers. Now, we're starting off simple. We're going to get more complex as we go, all right? Remember, we're not so much worried about the how. We're worried about the why, the underpinnings. Sort of like if you were to go down to the store and buy a piece of clothing. All you care about is what the clothing looks like, how much it costs, how it fits you, all that sort of stuff, right? You care about how you're going to wear it. You don't care about the process that it takes to generate the fabric that then gets sewn together. But for somebody down the road, creating fabric is a pretty big deal and is their entire livelihood, right? The weaving process, the dyeing process, all that sort of stuff. But you as the high-level user don't care. You guys so far has been high-level users of mathematics. We're going to delve down into the weaving process, what it actually means to do this stuff on a very base, nitty-gritty level. So we got a lot of definitions up front. On your notes, you should have your notes already filled in, and you're only going to have to really write on examples today. So I took away a lot of the writing. When it is time to write, I need you writing fast and furious with me. Sound good? All right. You can't see it, but they shook their heads. Okay. So first off, a postulate is a statement that describes a fundamental relationship between the basic terms of geometry, and postulates are accepted without proof. You will see this when we get there. These things are so basic that you really couldn't really create a proof for them if you wanted to. Very akin to those are axioms. Axioms are statements that are accepted as true. I could get really deep down into the difference between postulates and axioms, but for the purpose of making this lesson move forward, I'm not going to. Realize axioms, I mean, we're starting to get down to the very nitty-gritty level, stuff as simple as like 1 + 1 = 2, all that sort of stuff, okay? So axioms and postulates are the things that we're going to be using to build other things. A proof is a logical argument in which each statement you make is supported by a statement that is accepted as true. Now, here's the cool part about this. We're going to start off with just our base axioms and postulates. This is all that we have. We're going to then use those and churn them and apply deduction in order to make something else, and we're going to create a theorem. Then that theorem, once we've proven the theorem and we know that it is true, you can now use it to prove something else. And it's going to snowball. We can do bigger and better things as we go. Okay? So, theorem is a statement or conjecture that has been proven. We practiced making conjectures last class period. Realize, I hope you saw this, you can make conjectures that are false. And then counterexamples can be given. So we're going to be taking our postulates and axioms, combining them to make theorems that are always true, and there cannot possibly be a counterexample to them because of just the way that base logic works. Then from there, we'll be making our new theorems and moving forward. Also, a deductive argument is a proof formed by a group of algebraic steps used to solve a problem. Now, an interesting thing about theorems is that every single field, when you reach the terminal degree in that field, the farthest you can possibly go, it's called a doctor's degree of some kind. There's PhD, a doctorate of philosophy. There's MD, a medical doctorate. There's a JD, a Juris Doctorate, which in that case you don't call somebody who got a Juris Doctorate a doctor, you call them Esquire. And in that case you are a lawyer. You're an attorney when you get a JD. There's also, the most bizarre one I've seen out there is a PharmD, which is a doctor's degree of pharmacy, a doctorate of pharmacy. My brother-in-law, he is a professor at the Texas Tech Health Sciences Center over in Amarillo, and he is a professor of pharmacy. He has a PharmD. He's a pharmacist whose name is Dr. McCarroll, which sounds bizarre that you're calling a pharmacist doctor, but that's the way that it works, okay? And in mathematics, the way that you get a doctorate is essentially, it's not always the case, but in many mainstream collegiate universities, your avenue to getting your doctorate degree is to prove a new theorem. You've got to do a thesis, a dissertation, depending on what they call it at that level, and you're trying to create something new. You're trying to push a theorem out there that has gone beyond the realm of anything that's ever been done before in mathematics, which is bizarre because what that means is you essentially have to have an original thought, which sounds trivial, but when you look at it, all the thought processes that we have are based on all of our life experiences, so having an original thought is actually not as easy as people would think of. Most of the things that we go through are derivative. I had a professor who came running down the stairs one day all excited because the theorem that he proved for his doctorate had been placed in a textbook and named after him. It was actually listed in the textbook as Williams' theorem. And Dr. Williams was all super excited because somebody named the theorem after him, which makes sense because he proved it. But, all right, moving on. Paragraph proof is next. A paragraph proof is an informal proof written in the form of a paragraph that explains why a conjecture or given situation is true. This is going to be written in complete sentences, and you'll see why it's called an informal proof when we actually get to seeing a formal proof. All right. Now, here's our geometry postulates. There are 7 of them. All these are pretty much ones we've covered already as things that you can just accept for geometry. All right, 2.1, through any 2 points, there's exactly one line. We know that if I draw 2 points, only one line is going to go through them. If I could draw right and actually hit the dots. Okay, 3 non-collinear points, there's exactly one plane. Remember, non-collinear is important there, because if I have collinear points, I could pass multiple planes through them, as in the 2 different edges of a box. If those were 2 different planes, I could have 3 points on them, and those 2 different planes would all hit at the same line. A line contains at least 2 points, because if it didn't have at least 2 points, it would just be a point. It wouldn't go anywhere. Plane contains at least 3 non-collinear points. 2 lines lie on a plane, and the entire line containing those points lie in the plane. So basically, if A and B are on plane K, then the entirety of line M is on line K. It doesn't like bow up and then go back down. It stays directly on the plane. And then 6 and 7, what just happened there? 2 lines intersect. Their intersection is exactly 1 point. They're going to hit. They can't, double back and hit again. That'd be some sort of curve. But for straight lines, they hit exactly 1 point. and if 2 planes intersect, then their intersection is a line. And now, what you're actually seeing on your page is something more like this, just a list of all of our postulates. Now, these are going to be important because we're going to be using those over and over again throughout the unit. You're going to need to keep this page somewhere where you can see it, and I'm going to be referring back to postulate 2.3, 2.6 periodically, so it's helpful to have that where you can see it. So you'll notice, video people, you can't see this, but in my hand, I've got a list of mine that I've actually folded over, and I'm actually holding in my hand, supporting the tablet, so that I can see it as I go through, because I don't have these things memorized, okay? I've got to go use my reference material as we go through. So, this entire unit, have that thing handy, that way you can go through them. All right. First off, we're just going to worry about, can we explain that something is true using one of our postulates, okay? These are going to start off rather easy. So for example 1, points F and G lie in plane Q and on line M. We're wanting to show that line M lies entirely in plane Q. Could we show that using one of our postulates? You want to take a wild guess which postulate? Isaac, what do you got? Okay, that's a good observation. Planes Q and P intersect at a line. Now, I'm going to say in many of these pictures, there's going to be extraneous information here. Plane P is not referenced at all in what we're trying to do, so the intersection of planes is going to be beyond what we need to do right now, okay? But that is a good observation. All right? Here's what I'm looking at. 2.5, if you look back, says that 2 points lie in a plane, then the entire line lies on the plane. So, since points G and F are contained on plane Q, then all of line M must be on plane Q. I'm going to use postulate 2.5 to make this happen. Okay? Now, I'm going to put some text up here. Realize you don't have to copy this verbatim. Okay? This is a little bit too much here. But points F and G line on line M, and the lines lie on plane Q. Postulate 2.5 states that if 2 lines lie on a plane, then the entire line containing those points lies in the plane. Shows that this is true. Okay. Again, what I would expect to actually see you there, or see you write on something like this, is that 2.5 says that F and G are on Q. Therefore, line M is on plane Q. That would suffice, okay? Just showing me that you know that what you're talking about. Postulate 2.5 shows that line M is on Q. Now, the other reason I showed you these big old long explanations is showing that you can get a lot deeper and more detailed in the way you're writing things. Okay, there's always a deeper level. Okay, the rabbit hole always goes a little bit deeper. All right, just waiting for people to finish writing. All right. I'll give you all about 30 more seconds to finish copying. Okay. Example 2, we're wanting to see points A and C determine a line. Now let's look at our postulates that I gave you. You might need to flip back to look at them. Are there any of those postulates that can tell us that A and C determine a line? I'm sorry? 2.1? Through any 2 points, there's exactly one line. Good. All right. So points A and C are both on the side of a triangle. Means that they are on a line. Therefore, by postulate 2.1, they're going to be on a line. Here's what the actual overkill definition is. Points A and C lie along an edge, and the line that they determine. Postulate 2.1, which says there are any 2 points, there's exactly one line, shows that this is true.
Did you talk about a midpoint?
I mean, you could, but that might not be helpful here. I mean, yes, there is a midpoint of segment AC, but that midpoint's not going to get us to the point that there is a line. Postulate 2.1 is the simplest route. Can we give about 30 more seconds to copy? All right, next up, example 3. Refer the figure, I've sent directions to this before. Plane P contains points E, B, and G. So we got points E, B, and G. Yes, sir. Postulate 2.2 says through any 3 non-collinear points, there's exactly one plane. Okay, that one actually might have some merit there. Usually we're going to use that one, 2.2, to reference when we're like naming or referencing a specific plane, as opposed to the other way around, saying that it has points. Are there any of those postulates that talk about a plane containing points? 2.4, yeah. 2.4 says a plane contains at least 3 non-collinear points. E, G, and B are non-collinear, so 2.4 is the one we're looking for. Number 2.2 is when we're going to say that we're naming the plane or we're identifying a plane, whereas 2.4 is where we're going to be, wait, I might have said that backwards. 2.2 is where we're identifying a plane. 2.4 is where we are saying a plane contains points. Oh, and if you're wondering why I'm every now and then adding a dot to the screen, it's just on these long pauses. Whenever I'm editing a video later, it helps me see that the video hasn't stopped because dots are being added. All right, anybody start copying? All right. Line AB and line BC intersect at point B. AB and BC intersect at point B. 2.7, if 2 planes intersect, I'm not seeing planes intersecting, I'm looking for lines. 2.6, if 2 lines intersect, the intersection is exactly 1 point. Yes. And by the way, don't write all that out, because literally all of this stuff right here is all just a restatement of postulate 2.6. It's just restating it. So 2.6 tells us that. That's all we really need to know. All right, now our next set is going to be actually looking at the concept of is something sometimes, always, or never true. Because we want to be very careful of the idea that we don't go too far with a statement or with a postulate, to make it mean something that it doesn't, okay? We got to stick with what it actually directly says. So let's look at this first off. There is exactly one plane that contains points A, B, and C. First off, which postulate do we think might lend itself to this one? 2 point what? 2. Through any three non-collinear points, there's exactly one plane. That one actually looks pretty good. Here's the only problem with that one, though. It says through any non-collinear points. So it's true, and let me draw the intersection of two planes here. Through any three non-collinear points, like these three, yes, there's only one plane that goes through it. However, if I jump over to, say, these 3 points that I'm doing in green, then that doesn't work anymore because I've got multiple planes that go through those 2 points, or those 3 points. Okay, so collinear is important there. Okay, so that's a sometimes, because if A, B, and C are collinear, then they are contained in many planes. Now I just happen to draw 2. I mean, there's also another one that would go through like that and go through them. Okay, anywhere you could rotate around that line, there would be a plane there. So if they are non-collinear, then those 3 points are contained in exactly one plane. All right. Anybody start copying? Ma'am.
We're going to have to memorize the postulates.
Are you going to have to memorize the postulates? Actually, I haven't decided yet. Let me answer that question in 48 hours, okay? Next time I see y'all. Because I also want to make sure that I'm how do I say this? I have my feelings about it. I want to make sure that I'm on track with the rest of the geometry team, so I'm not expecting something different from y'all than the other geometry classes. All right. Number 6. Points E and F are contained in exactly one line. E and F. E and F, there's exactly one line. Really? Is there a postulate for that? 2.1. Through any 2 points, there's exactly one line. Yes. Postulate 2.1 directly says that. Okay, the first postulate states there's exactly one line through any 2 points. Now realize that even if I have, again, my 2 intersecting planes, and let's say that I've got points. Sorry, I'm in PowerPoint. It's harder for me to change colors in PowerPoint. Those 2, how in the world can I have a point that goes through those 2? Yeah, I got some people hand motioning at me. It goes diagonally across, right? It goes that way. And it would cut the box in half. Okay. Next up, 2 lines intersect in 2 distinct points, M and N. Always, sometimes, or never?
Never.
Never. Why never?
Because it's 2 points.
Because when they intersect, boom, they hit. I mean, look what it would look like if they're actually going to intersect twice. It would have to do something like that, and that's not a line, that's a parabola, right? So, but also, that is postulate, which one is it? Yep, 2.6. Says that will never, ever happen. Okay? Two lines L and M intersect. Two points L and M intersect. Sometimes? Why sometimes? Okay, because there are some exceptions here, right? They could be parallel. They could be skewed. Or they could be intersecting. So therefore we have our sometimes there. All right? And honestly, there is no postulate for that one. The closest one you could get to on that is postulate 2.6. But notice how 2.6 begins. If two lines intersect. If every single set of two lines intersected, that if would be unnecessary. It would say when two lines intersect or where two lines intersect. Okay. Anybody still copying? All right, points G and H are contained in plane M. Therefore, GH is perpendicular to plane M. Sometimes, never, always. First off, how is a line or a segment perpendicular to a plane? So we got our plane here. If a line were to come in and touch the plane and it were perpendicular to the plane itself, that would be the plane, or that would be perpendicular to it. Okay? Think of like a table with a leg sticking at the bottom. The leg is perpendicular to the plane. Okay? So G and H are on plane M. Let's just go ahead and call this guy plane M. Here's G, here's H, and so then we got segment GH. What do you think? Can that be perpendicular to the plane? Sometimes, always, never? Never. Do we have a postulate for that? Yeah, postulate 2.5. If 2 points lie on the plane, such as G and H, then the entire thing lies on the plane, and it'll be perpendicular to it, have to come off the plane. So that doesn't work. So this one is never. Never true. All right. So far that's just been practicing. Can we show properties are true? We haven't actually been doing any proofs here. We've been giving examples. Okay? Let's take a second and talk about what the actual proof process looks like. Okay? First off, on step number 1, we are going to list all of the information that we are given, and that could be multiple things. We'll see an example here in a minute where we're given multiple things that are told to us. Okay? And then, if possible, draw a diagram. Guys, drawing a diagram is huge anytime we have something geometric going on. Okay? That's going to help us organize our thoughts and be able to actually write out what's going to be happening there. Also, we want to, step 2, state the thing we're trying to prove. Okay? So you're going to see a lot of them start off with this idea. Given something, prove something else, and then we'll start going from there. You'll see that at the very beginning of a lot of these proofs. Step 3 is create a deductive argument. Remember, deduction is where we're using things that have already been told to us as true, postulates, axioms, etc., to form a logical chain of statements linking what we are given to what we're trying to prove. And sometimes there are going to be several steps in that process. There's actually a very famous one called Fermat's last theorem. Mathematician named Fermat I'm not getting into what that actual theorem was, but he said after they found him, he passed away, and in his study, a book was opened to a page, and in the margin of that book, it said, he had written down that I have thought of a wonderfully simple proof to this theorem. Alas, the margin is too small for me to write it. And so for hundreds of years, the question was, what was the proof he came up with? What was his theorem? How did he do it? And what they're looking for is this deductive argument linking one to the next. And everybody was looking for something that would happen, in like maybe a paragraph or two, something that's simple yet big enough that it couldn't fit in the margin of a book page. Well, it finally was proven in like the 1970s, I believe. Fermat, that happened to him in either the 16 or 1700s, 200 years later. But the proof of it, actually, when you actually wrote the whole thing out, was 180 typewritten pages approximately. And so it took that long to get from one to the other. Just one logical step after the next. Okay, and we'll get into how that worked later. Not nearly that deep, but realize it could be more than one or two steps here. All right, step 4, we have justify every single statement with a reason. You can't just say, I sort of kind of feel like something is true. You have to have a reason for it, and you'll see that as we go through our examples on those last few in your note packet. And then after we've made there, we're going to restate what we've proven to just emphasize the point and drive it home. Okay, so given that AC intersects CD, write a paragraph proof, also called an informal proof, to show that A, C, and D determine a plane. Now, what do we say we're always going to start with? Given, okay? So given that AC intersects CD, write that. Get used to writing it. You're going to write it a lot. What are we trying to prove? Next thing what we're trying to prove is that ACD is a plane. Now, remember what I also said, drawing a picture helps. So I'm going to do that up here. I've got line AC. Now, where am I going to put CD? Okay, so actually, let's be more specific. C, we already know where it is. C is right there. Where is D going to be? Anywhere you want, right? But can it be on the line? Could D be right there? Well, okay. So I like the way you said that. You said in order for it to be a plane, that's assuming the conclusion. We can't assume the conclusion here. We have to start with what we're given. Sir? Okay, yeah, that's it. The idea of intersecting. Because for it to intersect, intersection is the points that it shares in common, right? And so if D was on AC, the intersection would not be just C. It would be the entire line. Okay? So C is this. C goes there, and then, sorry, I'm going to erase this point D over here. D is going to be there. Now, what does that mean about A, C, and D? All three of those points. Boom, non-collinear, and then non-collinear will get us to, it defines a plane by postulate 2.2. 3 non-collinear points. All right, we've talked it through, now we just got to write it out. All right, so let's see. Since line AC intersects CD, then the intersection is at point C. That's where we started this whole thing, right? By the way, which postulate is that? Two lines intersect. Intersection is exactly 1.1. That's postulate 2.6. Since the lines have only one intersection, point D cannot be on line AC. Therefore, A, C, and D are non-collinear. And then by postulate, which one is that? 2.2. A, C, and D define a plane. So, ACD is a plane. Notice how I said that we're going to say what we're trying to prove at the beginning, and then we're restating it at the end. Now, was any of that like rocket science? No, it's all logical steps from one to the next, right? The problem is, how do we write it out in a way that doesn't take any sort of crazy logical leaps, okay? You got to practice this stuff in order to get it down, okay? Now, I'm going to give you all a second or two to finish copying that, because I'm about to erase it all and put something else up there that I expect you to not copy. All right. I'm about to erase my ink. In a few seconds. Sorry, I've got one more person copying right now. You good? All right. So, look at this. This is a different route of taking it. It's actually following the same route, it's just stated differently. Now, I'm not going to make y'all write this whole thing down. My point is that your answers are going to vary from everybody else's. By the way, one of the biggest clues that I get to students copying on this thing is verbatim, exact word-for-word answers, matching somebody else. Okay? It's going to be different. That's fine. It's expected to be. Okay? Just like if on an English essay, if you verbatim match someone else, it's pretty cut and dry. You copied, right? There's no way any two people are coming up with the exact same concept. All right. So, triangle ABC, BD is an angle bisector. Write a paragraph proof to show that ABD is congruent to angle CBD. What's the first thing that I'm writing? Given. Notice there are two things that I'm given here. I'm given that ABC forms a triangle, and I'm given that BD is an angle bisector. I need to write both of those down, because those both are important pieces of information to get my answer. Well, it's not an answer at this point. It's the process that's important. Also notice I've drawn a picture here. We got a triangle, and I drew an angle bisector. Now, what does bisector mean? Okay, I heard someone say down the middle.
It makes two angles congruent.
Yeah, it splits an angle exactly in half, right? So that each side is congruent to each other. Okay, that's the definition of it. So that'll come in important. That's why we got these two angle arcs marked here. Next, we're going to write what we're trying to prove. Angle ABD is congruent to CBD. And instead of me writing this one out, I'm just going to go straight to the one that I pre-prepared. But the route we're going to take is almost exactly that. The definition of an angle bisector is to cut an angle exactly in half. So, by definition, an angle bisector divides an angle into two congruent angles. By the way, definitions of words are always able to be used as fodder for proofs. Okay, a definition can be thrown in there. So since segment BD is an angle bisector, then angle ABC, which is our greater angle up here, is divided into two congruent angles. Thus, angle ABD is congruent to angle CBD. So before we move on to this, I mean, I know you're still copying, but I'm going to go ahead and throw out the idea of what do you think the odds are that the first time you attempt this, you're going to get it perfect the first time out of the box?
Really low.
Yeah, somebody said really low. I'd agree with that, okay? I just want to go and throw this out there because sometimes students forget about this. I mean, my kids are still young enough. I still remember teaching my kids to walk. Hopefully at some point you've actually seen a toddler trying to walk for the very first time. The first thing they got to do is they got to push themselves up and they balance on the edge of a chair or the edge of a stool or on their parents' legs or something. They balance themselves and they wobble, and then they finally get enough guts to let go. And the very first time that they let go, are they successful at bearing their own weight for an extended period of time? No, they fall down. They fail. But you know what their parents do whenever they fail? Come on, seriously, have y'all seen parents do this? What do? Do they come in and hammer, you messed up, you screwed up, how dare you do that? I expect you to walk right now. No. What did the parents do whenever the kid falls the first time of taking their hands? Yay, attaboy, good job, you're so cute. They encourage them through it, right? And then what does the kid do? Yeah, they fell in their diaper, which cushions them, but they laugh, they smile, they're getting encouraged, let's try that again. And then they fall, and they fall, and they fall until they can just stand there. Until eventually the next step is you'll walk in the room and you'll see the kid not leaning up against anything. They'll just stand up right in the middle of the room. Just stand up. And they'll hold that for like 10, 15 seconds, and they'll fall down. And you know what? You praise the snot out of them. Do we focus on the fact that they failed? No, we focus on the fact that they tried and they moved beyond where they were to begin with, right? Then you start getting to the actual walking phase, and it's just more rinsing and repeating of that, right? Every single time they try to take that step, it's actually better than it was the time before. Is failure wrong in that situation? No. Absolutely not. Failure is expected because failure is a teaching tool to get stronger, to get better, to learn what not to do, to learn how to balance, all that sort of stuff, right? And then, by the way, balancing while standing on 2 feet is very different than balancing while stepping forward, because you got to do that whole weight shift from one foot to the other, right? And you don't know that at first, but by failing, you learn. Guys, the first time out of the box, I expect you to fail. I know you're going to fail. Am I going to sit there pointing my finger and say, hey, you messed up on your proof? No. Guys, I am going to sit there and say, you know what? It's all right. You tried. You use that postulate. That's a good thing. Let's see how we can do it better. and we'll use it as a learning opportunity. Guys, please don't let the first time you fail on this be on the test. I would much rather you fail in a safe environment. Just like the first time that a tightrope walker fails at walking and balancing is not on a tightrope spanned across the Grand Canyon. The first time that he practiced balancing and fail was when he was probably a year and a half old while his parents were watching him in a safe, loving environment. Does that make sense? He got better and better until he could take the risk of walking across the tightrope. Guys, don't let the first time you try this be on the tightrope of test 2. Don't even let it be on the tightrope of the next quiz we're taking. Let the first time you fail be on the homework assignment. Come, ask me questions. We'll make it through. All right? Please try this stuff. You're going to fail. It's okay. Talk to your parents. They failed a lot at it when they were in middle school, in high school. All right? These proof things are not easy. Okay? It's all right to fail. All right. Moving on. Just to practice this, we're going to do it with some algebraic stuff because you all are used to doing algebraic manipulations at this point. An algebraic proof is one that is made up of a series of algebraic statements. By the way, anytime you're solving an equation, you are doing an algebraic proof. You're just not used to writing it out the way that we're going to write it out here, okay? This is a way to jump from buying the clothes to making the fabric, okay? Two-column proof, also called a formal proof, contains statements and reasons. Each step is a statement, and you have to write down the things your properties using to justify, and those are our reasons. Also, formal proof, yada, yada, yada. All right. This is another one you're going to be using quite a bit, so another one that I expect you guys to just kind of have on the side to be able to use. All these things, let's say of equality, I don't expect you to write that just because it's understood when we're talking about these things. I mean, when I actually write this out, if A plus B, then A plus C equals B plus C. It's this whole thing. If you have 2x equals 8, then you also know that 2x plus 3 is equal to 8 plus 3, right? That's how it actually gets used. And by the way, that's what you do every single time that you're trying to get rid of something in the solving process. It's something like that. The only one that's a little bit different is the distributive property, which you guys are used to doing distribution by now. All right. This is where we get a lot of writing, so please stay with me. Solve x plus 6 plus 2 times x minus 1 equals 30. Write justification for each step. This is already scaffolded for you. You have 2 columns, statements and reasons. So our first thing we're going to write off is the thing that was said in the problem. 6x plus 2 times x minus 1 equals 30. Now, we know for a fact that is true. How in the world do I know that was true? Because it said in the problem that was given. So let's write that down, and that one is given. All right, now, what's our first solving step on this problem? You want to take a wild stab at it? Okay, we can't combine like terms because of this parentheses right here. Yeah, that 2 times x and 2 times 1. What do I call that? Yep, so it gives us 2 times 6 plus 2x minus 2 equals 30. And that is the distributive property. Notice over here, I'm giving the reason as to why, this is the reason as to why I'm allowed to do that. All right, what am I going to do next? Okay, we say combine like terms. I realize combining like terms is not on that list I gave you a second ago. However, I do know, and I'm going to write this on the side just so you can see it, 6x plus 2x equals 8x. Right? Now, that substitution property of equality says that anywhere I see this, I can replace it with that. So I'm going to take this and replace it with that. I've substituted. So that is the substitution property of equality. And remember, I'm not going to require you to write of equality just for time's sake here. And now, what am I going to do next? Yeah. Going to add 2 to both sides. Now, we're used to doing that. I usually kind of do this whole thing down below. Ooh, gross. My battery's running low. All right, hopefully I'll finish. All right, I usually do that thing, right? For the sake of a proof, I need to actually be more explicit. I'm going to actually write a whole new line for it. And that's one of our equality properties. Whenever I'm adding something on both the left and the right to make it be equal and to balance the equation, that's our addition property of equality. All right, now what am I going to do? 30 plus 2 equals 32. So I'm going to write 32 on the next line. Which property is that? It's just what I did here, isn't it? Substitution. I'm substituting 30 plus 2 for 32. Notice I also did the same thing here. Negative 2 plus 2 is 0. So I'm substituting a negative 2 plus 2 for a 0, which I don't ever have to write plus 0, because it's understood. All right, what's next? Divide by 8. And what's the property there? Thank you. Division property of equality. It starts picking up once you see what's expected, right? And then our very last one is going to say x equals 4. And what's our property there? What am I doing? 32 over 8 equals 4, right? So that's the substitution property. All right. You got it 55, right? Okay, so I'm going to run through this one very quickly, okay? First step we're going to do, well, we write 2 times 5 minus 3a minus 4 times a plus 7 equals 92. Our first step is distribution. 10 minus 6a minus 4a minus 28 equals 92. That is distributive property. Then I got my combined like terms step. Negative 6a and negative 4a becomes negative 10a. And then minus 18 equals 92. That one was my substitution property. Then, again, just for brevity here, I'm going to write it this way. That's my addition property. And I feel like I've messed up somewhere here. Or maybe I messed up in last class. Anyway, that gives me negative 10a is equal to 110. And that is my substitution property. And then now I'm dividing by negative 10. That's my division property. And my last substitution, sorry, it's taking a while for this thing to load in. Dividing those three gives me a equals negative 11. And that's my substitution property. Sorry for the delay on the video, guys. But anyway, that's it. Let me go ahead and cut this before I dismiss my other class.